So we have been discussing the eccentrically loaded foundations, right? We just have the introduction. What is eccentricity load, or why do you need to study this eccentricity load? Okay.
Yes, sir.
Okay. So with the recap, I will discuss more about it. So let's see. We already know what is eccentric load, right? What is eccentric load?
If it is not working in the center of the column.
Sir, if the load is come to outside the center point of the column, then it's called the eccentricity.
Not only this, and if it is generating some flexural stress. Okay.
Yes, sir.
Whenever it is also generating some flexural stress. Okay. So why do you need to study this eccentricity? Okay, so let me give you one example. Suppose I already discussed in last class. Suppose you design this is a footing and this is a compression member. So whenever you find due to the eccentricity some portion of the footing is developing some tension. Suppose this portion of the footing is developing tension. So what happened? This portion is inactive.
Yes, sir.
Right?
Will
This portion is inactive. That means this is good for nothing for the footing. Only active area is this. So that time you need to know due to the eccentricity how much area of your footing is effective, and this area will be able to support the load that is your design for. You understand?
Yes, sir.
So here we can see that if we design that all the portion will take the compression and we distribute the load per unit area, right? So if you consider single strip, 1 unit area, single strip, so every single strip is transferring the load to the soil, right?
Yes, sir.
So instead of compression, if some portion is having tension, so that time this portion will not contribute to the load capacity. Opposite way, it will give some extra load to the foundations, right?
Yes, sir.
So this is a problem. So we need to know that due to this eccentricity, what sort of problem is there, right?
Yes, sir.
Okay. So if I just give you the review, we know that if there is a member, just for a review case, due to this load, there will be some flexural stress. And if we have some load like this, suppose as a compression, this is P, right? Maybe this is P prime. So you know, due to this load, it will deflect like this, right?
Yes, sir.
So this portion will have compression, this portion will have tension. So indirectly we will have, this is the sigma, right? Plus minus, this is actually sigma, right? And plus minus FB. What is FB? Flexural stress, right? You understand or not?
Yes, sir.
So how can you find the FB?
Sir.
So in
Into
general situation, we know that if in the solid mechanics we have studied, if we want to calculate the flexural stress of a structure, we consider FB equals to what? My by FB equals to My by I. Very good. Do you remember this one? FB equals to My by I. Hello.
yes, sir.
Okay.
Yes, sir.
So
Yes.
what is Y? Suppose if you take the stress on this portion,
Sir.
that is your Y, right? So what happened while
Yes, sir.
if we draw the stress diagram, you can see that the maximum stress is the edge of the footing, right? Edge of the structure, edge of the cross section. Suppose this is the neutral axis. Okay, so if this is the neutral axis, the portion or fiber you want to calculate, that is the amount of stress, right? So to get the maximum stress, we need to find in the extreme fiber, right? So this extreme fiber distance from the neutral axis we call what? C. We in basic solid mechanics we call it C, right? So that time we call MC over
Yes, sir.
I, and that is max. Do you get the point? Hello?
Yes, sir.
So for this C, what we can write? For this C, we can write C equals to H
It's by 2,
over
sir.
2, because C is just half of the height, right?
Yes, sir.
Okay.
Sir, here Y is distance from reinforcement to neutral axis.
No. From which fiber you want to calculate the stress?
Sir, if C,
Maybe here, maybe here, maybe
okay,
here,
sir.
maybe here. So which fiber you want to calculate the stress? That fiber.
Okay, sir.
Okay. So C equals to half of H, right? We know this total is H. So whenever we consider the C, it will be half of H. So in the both direction is same. So we know compression and the tension is equal from the very basic design. You have studied in the RCC also in the assumption of the design, while you develop the equation for beam design and others, right?
Yes,
Yes,
sir.
sir.
Okay. Then what you can do, you can replace this C equals to H by 2, right? Can we? Can you replace C equals to H
Yes,
by
sir.
2
Yes, sir.
and this I equals to
Yes, sir.
BH cube by
equal
12, right? Can you replace it? So
12.
if you cut
Yes, sir.
if we cut this portion, it would be 6, right? And if we cut this H, it would be 2. So finally you can write this 6 will go up, right? Finally FP equals to, you can write what? 6M over
H
what?
squared.
BH square, right? Okay,
Yes, sir.
is it okay?
Okay, sir.
So similar way, for the flexural stress, you can write 6M over BH square. Clear?
Yes, sir.
Okay. Have a look. Here we see that this is the compression. So this portion is compression, this portion is tension. This is tension, this is compression, right? So while we go for tension, what we do? We reduce, right? Because this is the compression plus and this is the tension minus, because we consider this is a compression member. Footing is a compression member, so that's why we consider compression would be plus and tension would be minus. So if you reduce this value, flexural stress, which is maybe tensile stress, so if you reduce this one, so if I consider this is sigma, okay, combined stress, sigma C. So for maximum we'll find this P by A plus this one, right? and for minimum one, what will happen? P by A minus this one, right? You understand or not this part? Because
Sir, is it minimum stress?
Yes, sir.
minimum stress in case of combined situation, because we do not first one is maximum combined stress. This is also combined.
Maximum.
First
Maximum.
one is a maximum.
Okay, sir.
Because while it is compression and this is also compression, right? So if you add this one and this one, so it is the maximum you are getting, right? While it is tension maximum, so you reduce from the compression. So this is in negative minus something, so this is tension. So you do not consider tension in the force in the footing. So that time we will draw the stress diagram for this is like that, and this portion we keep empty. Why? Because we do not consider any tension. If it is in tension, we keep it empty. You understand or not? Because this member or footing we consider will take only tension, only compression, no tension. Is that clear up to this?
Yes, sir.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Now if you understand this is a combined stress situation, so we know for axial stress that would be the scenery, right? This is for the P, and for M that would be the scenery. Okay, so this is in tension, this is in compression. So maybe this M is developed from this one. Maybe here is another load which is we call P prime. Suppose this is P prime. So we know, and this is suppose E distance, right? So we know M equals to P prime into E, right? So we can also write direct M. So this M will define what? P into E. Clear? Can you hear me?
Yes, sir.
Sir, why you consider P prime? Is it P?
No, P is the load is acting in the center. It might be like your
And P.
it might be your like gravitational load or self weight of the structures, something. You understand?
Okay, sir.
And P prime is load coming from the column. Just for an example, we consider. Okay, so this P does not create any movement. Is it creating any movement?
No, sir, because it is working in center.
Yeah, it is passing through the center
Like-
point. So that time it will generate uniform stress. But P prime, since they already denoted here M, that's why I'm just explaining you how does this M come here. So this M come from this kind of eccentric load. Okay, so due to this P, we got this uniform stress, and due to this P prime, which is eccentric load, which develops some rotational force, that is the bending force. So due to this, it develops some flexural stress. So this is in tension and this is in compression. So if you add these two, suppose this is 8 and this is 10, suppose. So we know this is minus 8. Why? This is in tension, right? So 10 minus 8,
Yes, sir.
how much? This is still compression 2.
2.
Okay, and this is 8 plus 8 because this is compression. This is 10. 10 plus 8, that would be 18. Is that clear?
Compression.
Okay. So similar way, when
Yes, sir.
when you find that E distance, because the only parameter is changing the moment value here is P. Sorry, E, because P is fixed. Okay, so if you find that E value is less than B by 6, if E value is less than B by 6, that time you will find the minimum stress is this much. There will be some sort of extension here, there is a minimum, and here would be the maximum. Okay, so the stress diagram would be like this. If you find E equals to B by 6, that time you will find in the edge the stress is 0. No tension, no compression. Are you getting the concept? It depends on the value of E. Okay? Okay. So why did I revise
Yes.
this portion?
Okay, sir.
Maybe I already discussed the one-way eccentricity problem also, right? But why did I revise it? Because you guys might be busy with RCC exams and other exams, so that's why you might have forget. So that's why I just revising. I'm revising just little bit. Okay. So is that clear to you? Please response. Hello.
Yes, sir.
Yes, sir.
Okay. So I already discussed this part. There are
Yes, sir.
several way
Yes,
to failure. Did I discuss this or not in last class?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Last class.
I also
Yes, sir.
discussed
Yes,
the
sir.
Carnot section, right? So now I think you know what is the importance of this Carnot section. If any load is transferring through this area with eccentricity, it will not develop any tension. Either it will develop zero tension or compression, little bit of amount compression, but no tension will develop in the footing. Okay, but if you exit this, that time is this different case. Okay, so in case of normal distribution, I already discussed.
Sir, few of us didn't get the point. What is Karn?
Carnot section is the diamond shape
Maybe.
where if you put the load, if you displace your load onto this line or inside this section, okay, so your footing
Okay. Yeah.
will not have any tension. Your footing will not have any tension.
So,
Maybe your stress diagram of this footing maybe like this. This is the minimum, or maybe like this. You understand? 0 here, here, but there should not be like this. This is what? Tension, and this is compression.
and
So
compression.
in Carnot section, if you have Carnot section, if you have the load inside the Carnot section, there should not be any hassle like this. There will be no tension.
Okay, sir.
Okay. So from this point of view, we already discussed Q max, that is the sigma max. So we just add. You remember that example I gave here, right?
Yes, sir.
So here you consider, I consider this is H. So you consider this is L, and this is B, right? So similar way you can put it here. Okay, and 6m over b square L. So this is for one-way eccentricity. For two-way, you will find another term here also. So we'll go to the two-way also. Let's see. So first let us discuss the one-way. So here you can see if this E value is less than b by 6, okay, so that time definitely the minimum value would not be 0. There will be some minimum stress and maximum. But if you find E is more than b by 6, okay, so that time you have some 0. Okay, that means this portion is in tension, but since foundation cannot take any tension, that's why they do not consider this tensile force. Okay, and this distance, if it is the situation, this distance they average, they consider in normal way, that is twice E. Is it clear to all? So if twice E is ineffective, if twice E distance is ineffective, this is the effective area, right? So this is B prime and L prime. Now the question is that when we consider the eccentric load is in this axis, that time we consider this much distance removed from the footing property, right? Or this much area will remove from the footing property. So this distance is in B directions. But if you consider the load is in the opposite axis, suppose you have a load here, right? Before you have a load in this axis, right? Now you are considering this part, so maybe you will have cut down like this. So this portion is what? Ineffective, right?
Yes, sir.
So for y-axis eccentricity, you will have this way, just opposite. You need to think, if you apply the load there, what are the area might have the tension, so that area you try to skip, but you have to follow some guideline to do this. Okay, after this is okay?
Yes, sir.
Okay, so these are the formulas I already discussed, how to calculate this eccentricity, how would the E value when it is equals to 6, B by 6 and so on. This is a very common discussion, I'm not going to repeat it. Okay, so there are a few methods that we can follow. So this is a very general methods, that is the Mayer-Hoff equations, we know. This is the methods of Mayer-Hoff equations, right? You understand or not?
Yes, sir.
Okay, so by this using Mayer-Hoff equations we can find out the effective area. Already effective area dimension is given here. And what is this effective area? B minus 2IC. So if this eccentricity is in B directions, so that time we consider B minus 2IC. But if it is in the Y direction, that time you will find this is in L by twice E. So that time L prime would be L minus twice E. Are you getting the concept? This is just opposite. Now maybe you are having the eccentric load on this axis, and which axis you are considering? B. Usually consider this is x-axis, right? Are you getting the point? Hello?
Yes, sir.
Okay.
Yes, sir.
So if this axis is x-axis, and now we consider this is the base axis, or not base actually, width axis, so that time we consider this dimension is B. So that time you consider B minus 2IC. But if you have load in y-axis, where we consider it's L-axis, so if load is only L-axis, that time we'll consider L prime is L minus 2IC. Okay?
Twice E. Yes, sir.
Okay.
The load will be in vertical edge. So how you will horizontally x-axis, y-axis, how you will denote it?
You do not understand then the footing. Footing is no vertical, no horizontal. Footing is in plane. This is your footing.
Yes, sir. But
So footing does not have any vertical and horizontal. You understand? This is your footing. So you apply load here, right?
okay, sir.
So that time you are having the area reduction in this side, because this portion may have the tension, right? Are you getting
Yes,
the point? So if you have load
Yes,
here,
sir.
Yes, sir.
if you have load here, right, so you have a chance to have a area reduction in this area. So that time you reduce this part. So while you have these
Okay,
directions,
sir.
so that time you are reducing the distance of L, so that would be L prime, and while you are in these directions, you are decreasing the distance for B, so that would be B prime. Okay.
Yes, sir. Now I've got the point.
Okay, so these are the common equations. Then you use the Prakash and Sharan theory to find out the similar way. Just use the formula. Okay, so bearing capacity factors under eccentric loading, this is for the one way, and Prakash and Sharan, they also develop for the rectangular foundations, which is this one. So you can also find out the shape factors. So for the shape factors, okay, and other factors, they already recommended some values, so you can use these formulas to find this. Okay, a continuous foundation is shown in the figure, right? This figure is for continuous foundation. So do you remember what is the continuous foundation? Do you remember that what is continuous foundation? Response
Sir,
please.
two,
Yes, no. If it
two
is
or
no,
more,
sorry,
two or more footing, sir.
no. So if you do not understand, no, then you need to explain or you need to study. Continuous foundation is like that, which is length is very high. Length is very larger than its width, right? I gave the example in class. Maybe this width is very small, 300 millimeter, but this is 20 meter long. So that time, if we divide by 300 millimeter, like 0.3 divided by 20, which is tends to 0. So this kind of foundation we call continuous foundations, right? Strip foundations, something like this. So if load eccentricity is 0.2 meter, so it is given that eccentricity is 0.2 meter. The foundation load, determine the foundation load Q ultimate per unit length of the foundations. Use Mayer of effective area method. Okay, so what does it mean? Maybe you have a foundation is like that, right? So this is your L, right? This is your L, and this is your width. So in this width, they did not they give the width is how much? 2 meter, right? This width is how
Yes,
much?
sir.
2 meter. Okay, so maybe here is the center of this width, so you have the eccentricity is 0.2. Okay, 0.2 eccentricity. Is it okay?
Yes, sir.
Okay,
Yes, sir.
so this is the scenario, and other soil properties are given. Frictional angle is given 40, and cohesiveness is given 0. So that means we can say it's a kind of granular soil, no frictional, no cohesiveness, right? It's a kind of sand soil. And gamma is given 16.5 kilonewton per meter cube. Okay, and depth of this given, that is df. Df is given how much? 1.5.
1.5.
1.5.
Okay, and this is our B, right? Is
Yes,
it
sir.
clear?
Yes, sir.
So we just need to use the Mayer of equation, so it's easy. So similar way we can find out the ultimate. So here what is the situation is required? Only the effective area. We use the area we have, that is different, right? So we need to find out the effective area. So we need to find out this B prime. So what will be the B prime without this? And this is our L, right? So here you can see usually we have three terms on this equation. C term is 0, since C prime is 0, so that's why the first term we consider 0. Okay, is that clear? That's why we consider the Q term and gamma term. Do you remember the formula? 3 terms on these equations.
Yes, sir.
Okay, so now we have to find all the information. So we know NQ, N gamma, NC can be found based on the frictional angle of the soil. So by using this 3.3 table we can get it. So since we don't have to calculate NC, we just need to calculate the NQ and N gamma, so you can find it easily. And then we can find out the B prime. What would be the B prime? What is the formula of B prime? You remember?
B minus 2E.
Very good. B
Looks
minus
like B minus 2E.
2E. Okay. So here you can see B minus 2E. So you get it. B prime is 1.6. That means this is the portion is effective for you. And by using these formulas, okay, there are also formulas that we use if in the mare of equations. You just use to find out this FQI, F gamma I, FQD, FQ, F gamma D. Okay, so then you find out this one based on the angle and based on the DF and B. So you can get it. Once you get it, you can find you can put all the values, but you do not know yet the Q, right? You do not know the Q yet, so you can find out the Q. So you can find out this Q like this. Here you can see 16.5 is the unit weight gamma, right? And this is the DF. So if you multiply, you will get the stress Q. You understand or not? You understand?
No, sir. No, sir.
This is 1.5 and this is 16.5. So if you multiply 1.5 and 16.5, this is the unit weight, right, per volume. So if you multiply it one distance, so it is giving you per area. So weight per area is, or load per area is what?
Stress.
Stress. So Q is stress. Now it's okay. Newton per
Oh,
meter.
yes, sir. Yes, sir.
Okay. So see, once you have all the information, you just put it here and you get it. And now you can find out the Q ultimate. And one important thing is here. Do you remember that while we consider the slab design, we consider the unit strip, right, in the slab design?
Yes, sir.
Do you remember or not?
Yes, sir. One unit strip.
One unit strip we consider, right?
Yes,
So what is the equation or what is the information we develop for this strip? We continue here. We continue the whole portion, right? So similarly, for the continuous footing, maybe we consider this unit strip, and after that we continue for all. You understand? So that's why for L we consider L prime as a 1. Now is it clear why do you consider L equals to 1?
Yes, sir.
Okay, so for 1 unit dimension of L we can get it. Okay, so today we'll not take any break. Maybe we can leave 15 minutes before. Okay.
Okay, sir.
Okay, so is there any doubt on
Okay,
this
sir.
one way?
Uh,
No doubt,
one
right?
written person because the sir,
Yes,
sir, because the foundation in question is continuous foundation.
yes.
B prime by L prime is 0, sir.
Mm.
Sir, what do you mean by that, sir?
Uh-huh.
Sir, that line, sir, because the foundation is in question is a continuous foundation. B prime by L prime is 0.
Yeah, I already explained here. So if it is consider this is a foundation, suppose for continuous foundations, what does it mean? Suppose you have the distance is 0.3, suppose, and this distance is suppose 10, just for an example. So 0.3,
The ratio is almost 0.
yes, 0.3 divided by 10. So what is the value? So it's almost 0, right? So it would be
Yes, sir.
0.03, right? You understand?
Yes, sir.
Okay. So in this scenario, you can find it. So the length of the foundation is very high compared its width. So that's why we consider this ratio is equals to 0. And when it's equivalent to 0, that time we consider it is what kind of foundation? Continuous.
Continuous foundation, sir. Continuous foundation.
Okay. Any more doubt?
Yes, sir. No, sir.
Okay.